Hello everyone, and thank you for tuning in to listen to my talk. I'm very grateful to CASCA for this golden opportunity to present my research to such a broad audience. So this is a talk about white dwarf stars, and more specifically about the atmospheres of cool white dwarfs. So this might sound like a narrow topic at first, but as you will see, there are actually many connections with other interesting fields of both physics and astronomy, so I'm sure there's something for everyone in this presentation. According to most recent estimates, 97% of stars in our galaxy will end their lives as white dwarfs. So it's the stage that is reached once a star has exhausted all its nuclear fuel on the main sequence and during the giant phase. So it's this little tiny core that is left behind after the planetary nebula phase. 99% of the mass of a white dwarf is located in its core, which is usually made of carbon and oxygen. And this core is surrounded by a helium envelope and a very thin hydrogen layer. The physical conditions encountered in white dwarfs span a wide range of temperatures and densities. So in the center, we're talking about typically 10 to the 6 gram per cubic centimeter and a few million kelvins. As for the atmospheres, it ranges from a low density ideal plasma all the way to something more akin to a liquid. To me, one of the most compelling reasons to study white dwarfs is that there are just so many things we can learn from them. One of the things we can do with white dwarf is that we can use them to measure the ages of stellar populations. So because white dwarfs have already exhausted all their nuclear fuel, the only thing they can do for the rest of their existence is to simply cool down until they become a black dwarf. Now, because this cooling process can be modeled and because we can measure the temperature of a white dwarf using spectroscopy, it means that we can infer the cooling age of a white dwarf. If we add this cooling age to the main sequence lifetime of the white dwarf, we get its total age, which can be used to trace the age of a stellar population. To go in more details, we also need to worry about the mass of the white dwarf and also about its atmospheric composition, because those are two parameters that will affect the rate at which the cooling takes place. But the important thing here is that those three parameters can be constrained from spectroscopy, photometry, and parallax observations. So using this technique, it has been possible to measure the ages of the major components of our galaxy. And if you have a volume-complete sample of white dwarfs, you can even go further and infer the stellar formation history of our galaxy. Now, I want to emphasize that this is a very unique property of white dwarf, that it's so easy to measure their ages. If you look at main sequence stars, for example, their observable properties change very little over time, which means that you end up with large uncertainties if you try to measure their ages. I mean, even for the sun, for which we have exquisite observation, we still have to rely on measurements on meteorites to infer its age. So really, this is a very powerful property of white dwarfs. Now, another very interesting thing we can learn from white dwarfs is that we can use them to measure the compositions of planetesimals outside our solar system. So let's see how this works. So about a quarter to a half of all white dwarfs show traces of heavy elements in their spectra. So we're talking here about elements such as iron, calcium, sodium, and magnesium. This was initially a problem for white dwarf theory because those elements are expected to sink relatively rapidly below the photosphere of a white dwarf. So given the fact that white dwarfs have typical ages of billions of years, those elements should have ample time to diffuse out of the photosphere, so really we should not see them anymore. The solution to this puzzle came relatively recently, and it's that those white dwarfs that show heavy elements have recently accreted or are actively accreting planetary debris from planetesimals that were torn apart by the tidal forces of the white dwarf. So according to this scenario, you can have minor planets, asteroids, comets, etc. that survive the post-main sequence evolution of their host stars. So once the star reaches the white dwarf phase, well, some of those planetesimals are still around, and for one reason or the other, their orbits can be destabilized, they come too close to the white dwarfs, and then the tidal forces just tore them apart, and eventually they are accreted onto the white dwarf. So not only does this scenario explain why we see heavy element spectral lines in white dwarfs, but it's now also supported by the detection of dust disks around white dwarfs, as well as the detection of a few transiting planetesimals around white dwarfs. So how do we measure the composition of the planetesimals that were accreted by white dwarfs? Well, we do this using spectroscopy. So the idea is just to fit a high-resolution spectrum using atmosphere models, and then your best fit gives you the photospheric abundances, which you can then translate in terms of the initial planetesimal composition, given that we know at which rate the different elements sink into the atmosphere of the white dwarf. So once you know this, you can compare the composition of your planetesimals to that of known solar system bodies. And that way you can tell, for example, if you have more volatile elements, then you can conclude that this is maybe a comet, or if you have more heavy elements like iron, then this could point to a planetesimal that has a differentiated composition. So there's really a lot of science you can do with those measurements. An interesting historical side note is that actually white dwarfs were the first object to provide us with the first evidence of the existence of exoplanets. So this evidence came as early as 1917 from the white dwarf Van Manen II, which is the third closest white dwarf to us, and it's also the third white dwarf to have been discovered. So if you look at the spectrum of Van Manen II, you can see those two little dips over here, which are actually calcium 2H and K lines. So we now know that the only way to explain the presence of those lines in the white dwarf is that the white dwarf must have accreted a planetesimal from its planetary system. So it's quite funny actually to realize that more than 100 years ago we already had the first direct evidence of the existence of planets around other stars. Now, a third interesting thing that we can do with white dwarfs is that we can use them as laboratories for extreme physics. So because white dwarfs reach such extreme conditions, and in particular such extreme densities, we can use them to test physical theories that we cannot test in the lab on Earth. So one of those theories concerns strongly coupled plasmas. So it's predicted that if you cool down enough a very dense plasma, at some point the ions will be so correlated that they will be trapped into a lattice structure. Now, this phenomenon is predicted to also occur in white dwarfs, because as a white dwarf cools, its core also cools, and it's dense enough that at some point it reaches the conditions where we think that this liquid to solid phase transition occurs. And this is what we refer to as a core crystallization. So this is no longer just a theory, because it's actually possible to observe the signature of this phase transition. So the key here is that during this liquid to solid phase transition, you have the release of latent heat. So this is a new source of energy for the white dwarf, which means that it will cool down more slowly while you have this release of latent heat. And this as a signature in astronomical observations. So here I show you how many white dwarfs we have per bin of luminosity. And you can see that there's a bump over here, and this bump is exactly where we expect the core crystallization of white dwarfs to occur. So the explanation here is just that when white dwarfs come through this region, there's release of latent heat, so they evolve more slowly. So it's normal that we see a pileup of objects in this region. So for the moment, this pileup is still not so well modeled, but it's a very nice example of an interesting interplay between physical theories, so here dense plasma physics, and astronomical observations. So we can use astronomical observations of white dwarfs to better constrain this phase transition of plasmas, and we can also use our knowledge on these phase theories and on simulations of these phase transition to better understand the astronomical observation that we have. Now, I should add that white dwarfs are not just tools to learn stuff, other interesting stuff. They are also very interesting objects in their own right. So there are many puzzles that we still have to solve with white dwarfs, and here I would just like to talk a bit about one of those puzzles, so the spectral evolution of white dwarfs. So spectral evolution refers to how the atmospheric composition of a white dwarf changes through time. So we could expect naively that if a white dwarf has hydrogen, then its atmosphere will always show up as being hydrogen rich. But in fact, there are many different processes that compete. And so during the evolution of a white dwarf, its atmospheric composition can change as the importance of those different physical processes become more important or less important. So if you look at very young and hot white dwarfs, they are basically all dominated by helium, just because everything is mixed up. So even though you may have a little bit of hydrogen, there is so much more helium than you would see mainly helium-rich atmospheres. Then if you go to lower temperatures, the complete opposite happens, so you only see hydrogen-rich white dwarfs, and this is due to gravitational settling. So basically, the white dwarf had enough time for the hydrogen to float up on the top of the helium layer. Then if you go to even lower temperatures, you start seeing helium-rich white dwarfs again. And this is due to the convective dilution process. So there's a convection zone in the helium layer that reaches the hydrogen layer. So it slowly dilutes the hydrogen layer in the very thick helium layer beneath it. At even lower temperatures, this process continues, so you have more helium-rich white dwarf, and in this case, it's accelerated by convective mixing, where the convection zone of the hydrogen layer merges with that of the helium layer. So now you can really mix your thin hydrogen layer with the deep, the thick helium envelope underneath it. If you go to even lower temperature, it seems like this process is reversed, and you have more hydrogen-rich white dwarfs. So we still don't understand what's happening here. And if you go to even lower temperatures, then it's not even clear what is the ratio of hydrogen to helium-rich white dwarfs. So this is a very simple picture of the spectral evolution of white dwarf. There are many more details that I've ignored here, but just to give you a sense that, I mean, we still don't understand all there is to understand about white dwarfs themselves. And about this part here at cooler temperatures, I'll come back to it later on in this talk. Now, it is important to realize that all the applications I have discussed so far depend to some degree on the use of white dwarf atmosphere models. So we need those atmosphere models if we want to measure the temperatures that we need to determine the ages of all the white dwarfs. We also need those models if we want to measure the photospheric compositions that we need to measure the composition of planetesimal accreted by white dwarfs. So really, we need atmospheric models to measure the most basic properties of white dwarfs in about every possible application. So the way we use white dwarf atmosphere models is that we give as an input the atmospheric parameters, so temperature, the atmospheric composition, and the surface gravity. From those parameters, we can compute as an output the wavelength-dependent emergent flux, and then we compare this synthetic spectrum to the observed spectrum, and if we have a good match, then we can say that the atmospheric parameters that we use as an input are close to the actual atmospheric parameters of the white dwarf that we are analyzing. It's important to keep in mind that actually white dwarf atmosphere models also depend on a lot of physics. So opacities, equation of state, convection, radiative transfer, chemical equilibrium, and of course the quality of the emergent flux that we compute depends on the quality of the input physics that is implemented in the white dwarf atmosphere code. Now, this is not a problem for most white dwarfs, but it turns out that it's quite a big problem for the coolest, oldest white dwarfs. So the input physics become very uncertain for those objects. So let's see now why this is the case. So the problem with cool white dwarf, and especially with helium-rich cool white dwarfs, is that they have a very transparent atmosphere. So let's see why this is the case. So let's look first at a normal temperature, warm helium atmosphere white dwarf. So if you have a warm atmosphere, it means that you have many electrons in the atmosphere. And this means that you can have a lot of helium minus free absorption, which is the dominant source of opacity in those objects. So if you have a lot of this kind of absorptions, it means that photons that come from deep into the atmosphere cannot come directly to us. They are blocked before they do so. So the photons that we are able to observe only come from the upper region of the atmosphere, where the density is relatively low. Now, if you have a very cool helium-rich atmosphere, you have fewer electrons, which means less helium minus free. So the atmosphere becomes very transparent, and the photons that we observe come from very deep in the atmosphere, where the density is higher. Because the density is higher, it becomes much more challenging to model, and this is basically from where all the problems come from. So to give you a sense of the physical conditions we are dealing with, I've plotted here the density, temperature profiles of the Sun, Jupiter, and a cool white dwarfs. And in each case, the circles here, they indicate the location of the photosphere of those objects. So that is the region from where the typical photon comes from. So what you can see is that the conditions we're trying to model in cool white dwarf atmospheres are much more extreme than what you would see in a more typical stellar atmosphere. So the densities are much higher. In fact, we're talking about conditions that are more similar to what you would find in the inner layers of a giant planet. So because the density is higher, it comes with a lot of complication. It means that many approximations that are usually implemented in stellar atmosphere code are no longer valid because the ideal gas law is no longer valid. So you need to revise all the input physics, so the opacity, the equation of state, and the chemical equilibrium to make sure that you properly account for all those interactions between particles that occur at those fluid-like densities. So just to show you more visually why we need to take those effects into account, here are three examples, so three cool white dwarfs. So you can see in black the observed spectrum. The dashed green line shows the best fit model. So you can see that in each cases the fit are very poor, and this is because those models don't take into account all the high density non-ideal effects that arise into those dense fluid-like atmospheres. So this really motivates to revise those atmosphere models to include those effects, because when you have such poor fits, you cannot trust the parameters that you determine, which means you cannot reliably measure the age or composition of those objects. In the past, people had to rely on some clever analytical calculations to try to take into account those non-ideal high-density effects. Now, there are some tools that have been developed in the context of condensed matter physics that can be used to take those high-density effects into account using a first principle approach. So the idea beyond those tools is basically to just go with the most basic laws of physics, so quantum mechanics, classical mechanics, to simulate the behavior of a system of atoms from first principles. So as few approximations as you can. So let me just give you an example of such calculation that I had to do for my thesis. So there are many different types of first principle calculation, but this is a very illustrative example. So I was interested in computing the time variation of the dipole moment induced during collision between hydrogen molecules and helium atoms in the atmosphere of cold white dwarfs, because this gives rise to an important opacity in cold white dwarfs. So to simulate this this induction of dipole moments, what I did is that I used DFT molecular dynamics. So the idea is that you just place your ions into a box, and then you use an equivalent of the Schrödinger equation to compute the distribution of your electronic density. And from that electronic density, you can compute a potential function, which you can then use to apply Newton's second law to evolve the system by a small time step. And then you repeat this again and again until you have some long enough trajectories for your particles to look at whatever you are interested in. So this allows to really simulate a system from the first principle of physics. And it's important here to realize that this kind of calculation requires a lot of computational time. And this is why it's only recently that those tools have become more and more used in many different contexts of physics. So now let's look one by one at those fits, and let's see how this improved physics from ab initio calculation can improve the agreement with the observations. So this is the first example. So in this example, the problem with previous models was that when we were trying to fit those ionized calcium lines, the models were also predicting this very strong neutral calcium line, which we just don't see in the observations. So the problem here had to do with pressure ionization. So pressure ionization is when you put an atom in a dense medium, and this medium pushes the outermost electron out of the atom, so it ionizes the atom by pressure. So pressure ionization was included in previous white dwarf atmosphere models, but it was included using a pretty crude hard sphere formalism. So I've devised a way of accounting for pressure ionization using only first principle physics, and when I do so, I find a fit that, as you can see, is in much better agreement with the observations. And I want to emphasize here that there is no free parameter in this new implementation of pressure ionization. So really everything comes from first principle physics. So it's really satisfying to see that at the end, you do find a much better fit. My second example is a white dwarf that, like the other one, has accreted a planetesimal. So that's why it shows some calcium lines, iron, magnesium, MgH band, and a very wide and strong sodium line. So previous models were doing a very poor job, and here the problem had to do with the absorption profiles that were used to describe the spectral lines. So if you have a low density atmosphere where there's a large separation between the atom that absorbs the photon and the perturbing atoms around it, then it's fine to assume that this interaction follows a van der Waals potential. And when you do this assumption, then you can describe the absorption profile by a Lorentz function. But this is no longer true at high density, because then the separation between the perturber and the absorbing atom will be much smaller. And at small separation, you can have strong deviations from a simple van der Waals potential. So you're not really well capturing how the shape of the spectral line is supposed to be. So this kind of potential can be obtained from first principle calculation once again. And when you do this, and when you compute new spectral line profiles, well, you find, once again, a much better fit to the observation. And this really matters because this means that now, for this star, we can precisely measure the abundances of the different elements that we detect, which means that we can now know what was the composition of the planetesimal that was accreted by this object. And in this particular case, it's still a puzzle because the planetesimal that was accreted by this white dwarf was very sodium-rich, and in fact, there was no body in our solar system that has a composition that comes close to the planetesimal that was accreted by this white dwarf. My third and last example is not a white dwarf that has accreted the planetesimal, but rather a white dwarf that shows molecular carbon bands. And this carbon actually comes from the core of the white dwarf, so it was brought up to the atmosphere by convection. So here, previous models were poorly describing those molecular bands. So to understand what's going on here, I first have to mention that those bands are the results of three simultaneous transitions. So you have electronic transitions, rotational transitions, and vibrational transitions. And here the problem was that it was not taken into account that at high densities, this emergent spectrum is completely distorted because you have all this helium that pushes around the carbon molecule. But once you do take this into account, you find, once again, a much more interesting fit. So I hope I've convinced you with those three illustrative examples that the improved input physics from first principle calculations yield much better fit to the observations, which means that now, for the very first time, we can really trust the atmospheric parameters that we determine for those white dwarfs. So let's now move on some applications that are possible with those new models. So the first application I'd like to discuss relates to the spectral evolution of cool white dwarfs. So I've mentioned earlier that the spectral evolution is very poorly constrained for cool white dwarfs. So let's now see why this is the case. So the problem essentially all comes from the fact that both hydrogen and helium no longer show spectral line in white dwarf spectra when you go below 5,000 degrees. So the reason for this is that there's just no longer enough thermal energy to excite the transitions that we can see in the visible part of the spectrum. So because of this, it becomes very hard to determine the atmospheric composition of those objects because we cannot simply look at which lines we see and from there infer the composition. But there's a way around that. So what we can do is that we can look at the photometric observations, so the spectral energy distribution, and we can exploit very small differences between hydrogen and helium-rich spectral energy distribution. So those differences arise from the different continuum opacities between hydrogen and helium atmospheres. And I show here an example of how this can be done. So the arrow bars represent the observations. The black circles represent the best fit, assuming a hydrogen atmosphere, and the open circles show the best fit, assuming a helium atmosphere. So in this case, we would say that this is probably a hydrogen-rich white dwarf because the black circles appear to yield a bit better fit than the white circles. Of course, this can be quite tricky because we're exploiting very small differences between both compositions, and this means that you really have to trust your models if you want to do this. But now that we have newly improved models that we have extensively tested, well, this is something that we can do while standing on a much firmer ground than previous studies. So previous studies that have looked at that have found vastly different conclusions for reasons that will become more clear. So if you look at what is the fraction of white dwarfs that have a hydrogen-rich atmosphere below 5,000 degrees, you can find answers ranging from a minority of them to almost all of them. So, of course, this problem comes from the fact that we are exploiting very small differences. So if you don't use the same models, if your model physics is not right, then you will find completely different conclusions. And those differences do matter because if you look at the cooling of helium and hydrogen atmosphere white dwarfs, they don't cool down at the same rate because a hydrogen atmosphere is much more opaque than a helium atmosphere. So if you make an error on the atmospheric composition, you could be making an error of the order of 1 billion years on the cooling time of your white dwarf. So this is really something that matters beyond the study of spectral evolution. So the problems with those studies is either they were not including the most important non-ideal high-density effects in their physics, or they were included some of those high-density effects, but not for metal-polluted white dwarfs, so they were restricted only to a subset of the whole diversity of white dwarfs. So we have revised this question using our new models and an unbiased sample. And we find a solution that is basically between the previous studies. And it allows us, among other things, to say that the accretion of hydrogen from the interstellar medium does not lead to all white dwarfs to be transformed into hydrogen-rich white dwarfs as it was proposed in the past. So on this, let's move to a second application of the new cool white dwarf atmosphere models. So I'd like to discuss a bit of the composition of planetesimals accreted by white dwarfs. So on the histogram here, I show the magnesium to calcium abundance ratio measured at the photospheres of white dwarfs. So the results that you see here come from the largest sample analyzed to date of white dwarfs that have accreted planetesimals. So you can see that the peak of this distribution matches the composition of CI chondrites. So CI chondrites are meteorites that have a composition that is very close to that of the original solar nebula. So we expect that on average, the composition of planetesimals accreted by white dwarfs will be very close to that of CI chondrites. So it might seem like a logical result that the peak of the distribution matches the composition of CI chondrite, but actually it's kind of a puzzle because if you accrete, say, magnesium and calcium into a white dwarf atmosphere, the magnesium is expected to sink more slowly than the calcium, which means that actually you should see that the peak of your distribution should be at a higher magnesium abundance than what is measured in CI chondrites because of this differential diffusion. Now, if you look at the fits of the white dwarfs that were used to infer this distribution, we can find many problems, especially with the magnesium triplet, which indicates that maybe there's a problem with the magnesium abundances that were measured for those stars. So I have revisited this study, revisited all those stars with the new models. So the first thing with the new models is that we have much better fits to the observation, and this gives us more reason to trust what we find with the models. And indeed, we find a distribution that is shifted by about what we expect from differential diffusion, so that it's now consistent that those white dwarfs have accreted chondrite-like planetesimals with a chondrite-like composition. So it's time to move to the conclusions. So I have 3 points basically. So the first point is that we have improved cool white dwarf atmosphere models using simulation techniques that were initially developed for condensed matter physics. We've shown that this new physics allows the models to yield much better match to the observations. So I did not have the time to go in this presentation, but I don't want to give the impression that everything is solved. There's still a class of white dwarf known as ultra-cool white dwarfs for which we still have problems with the fit. But anyhow, this is still a big step in the right direction. So using those new models, there are now many applications that are possible. So the first one is that we can determine more accurate ages for the coolest, oldest white dwarf. We can precisely characterize their spectral evolution, and we can much more accurately determine the composition of the planetesimals that they have accreted. Before moving to the question, I'd just like to say a big thank you to all those who have made this research possible, and in particular to Patrick Dufour, my PhD advisor, without whom none of this research would have been possible. Thank you.